My name is Karl Lewandowski, and I'm a postdoc at University of Glasgow. And today I'm going to talk about my research regarding incremental cold flow forming processes. So this is a relatively new manufacturing technique which allows for forming axisymmetrical components. As you can see from the video, it uses a series of rollers that compress and stretches a preform through consecutive stages over a rotating mandrel. So parts produced by this process have a very high precision. They are ready to install. Therefore, they require a very short processing time. They also offer improved mechanical properties and reduced thermal load. However, due to the nature of this process, including extreme plastic deformations, contact with the series of rollers, heat dissipation, it has been exceptionally difficult to simulate, and thus not allowing the industry to take the full advantage of this technique. Traditional approaches typically utilize the explicit time integration, so they are only conditionally stable. They also have Lagrangian formulation, so physically moving the mesh in order to simulate the rotation, which for high rotational velocities demands very small time steps. They use classical nested plasticity approach that requires often remeshing and projection of internal variables, compromising the accuracy. And all of that makes them computationally expensive, and therefore they do not offer sufficient accuracy and robustness for this engineering purpose. So our aim is to develop new algorithmic strategies towards plasticity that will enable simulating the complex forming processes. The goal is to have a method that is implicit and stable, is formulated in the arbitrary Lagrangian Eulerian formulation for simulating the rotation properly. It's modular, so we can easily add additional physics. And finally, is open source using our finite element library MoFEM developed at the University of Glasgow. So let's start. We will consider an isotropic elastic body under prescribed body forces, boundary conditions, and displacements. And as usual in mechanical problems, we have to satisfy the balance of momentum. In case of plasticity, the material properties depends on the current stress state, and the distinction between purely elastic and elastoplastic is determined by the so-called yield function. Here we use the well-established von Mises yield function that is suitable for modeling metals. We assume that the total strain can be decomposed into elastic, so irreversible, and plastic irreversible strains, which is a typical for small strain formulation for plasticity. Following the principle of maximal dissipation, a flow rule can be derived, which basically tells us about the evolution of the plastic strain. So here you can see the tau is plastic multiplier, also often called consistency parameter, and n is the flow vector defined as follows. And the plasticity model is completed giving the conditions on the consistency parameter and the yield criterion, which are often known as a loading and unloading conditions. So our idea of the multifield approach is to use these last two equations as a constraint for our conservation of linear momentum and solve this whole system as a coupled problem. Before we can solve the system in a weak sense, we need to get rid of these inequalities of loading and unloading conditions. There are many ways to do it. We decided to use the established so-called complementary function like this. It is very often used, for example, in contact mechanics. And as you can see, it uses this max function that we can then simply expand with the absolute, and we get this one simple equality that we can then directly plug in into our global system. One disadvantage might be that it introduces this parameter Cn. Although these conditions are satisfied regardless of the choice of the Cn, we only have to keep in mind that this should affect only the stability. And usually in literature, what was established that if we choose this parameter to be the inverse of the Young's modulus, then everything should be fine. So the weak form for our finite element is derived by Galerkin, standard Galerkin approach, resulting in the following set of discretized equations. So to approximate the primary variables, which in that case will be the displacements, plastic multiplier, and plastic strains, we will use the hierarchical shape functions provided by MoFEM. And please note here that the displacements is in H1 space, so it means it's continuous, and plastic strain and plastic multiplier are in L2 space, so it means they are discretized discontinuously. And this is a more detailed definition of what it means, L2 and H1 space. So in L2, the norm of the function is bounded, and H1, the norm of the function and its gradient is bounded. So linearization of the system for Newton method in this case is rather straightforward. Note that we only have to compute the partial derivatives of our residual expressions for all the three governing equations for displacement, plastic multiplier, and plastic strains. Typically, classical nested approaches, they solve the evolution equations via local Newton method on the integration point. On the integration points with the algorithms like closest point projection, and then use another global Newton solver to solve the entire system for displacements. But in our approach, we are not using that. Any of these algorithms are not necessary because we are solving for displacements and plastic variables simultaneously in one monolithic Newton-Raphson scheme. One more thing to also note is that we also incorporate the implicit integration in time, which will be necessary later for LAE formulation for rotation. And to present that our formulation works, I will start with a very simple example that of a specimen that undergoes cyclic loading. So as you can see, the model can properly handle loading and unloading behavior typical for perfect plasticity without any problems. We can also add kinematic hardening, and we get the results as well, like predicted by the plasticity theory. If we look at the nonlinear solver iterations, we can see in these three columns the residuals of our three fields, primary variables, plastic strain, multiplier, and displacements. And because we are using simple smart string kinematics, something happened because I can hear myself. Someone switch off the microphone. Okay, I will deal with that. what we can see here is the first residual for displacements is converging basically in one step, because we are using linear elasticity in that case. But as the title promised, we will employ the large strain formulation. So for this, we will use the kinematic formulation proposed by Professor Mie in this paper. This approach makes it possible to extend classical small strain constitutive relation into finite strain setting. It's particularly applicable, useful when we deal with large rotations and moderate strains, which will be great for our plasticity. So as you can see, it introduces this Henke strain measure, which is the logarithm of the product of the gradient of the deformation. And what is great about it is that it still preserves the decomposition that we used previously for small strains. And it also introduces the dual stress measure T. So the way this framework works is that we use the geometric post-processor on our strains, and then we plug it into our small strain model. It doesn't have to be multiplasticity, it could be classical. When we replace the small strain with this Henke strain measure, and then our Cauchy stress in small strains will become this strain, the stress measure T, which doesn't have a physical meaning, but afterwards we use this geometric post-processor that basically recasts this to the first Euler-Kirchhoff stress that you can use directly in our balance equation. And thanks to this framework, we can reuse 90% of the code for small strains. So deriving the new weak form is straightforward. We only have to change the stress measure, and remember that now we are solving for plastic for logarithmic plastic strains. But we don't really have to change anything in the code. Just in the post-processing, we need to know what we solved for. To test this new formulation, let's consider a classical pooling of axisymmetric rod example, where the plastic necking is triggered by introducing the imperfection in the middle. This example from the literature uses the combination of linear and saturation type isotropic hardenings. You can see the parameters here. And from the solution, we can observe that the necking is occurring in the middle as expected, and that you can see that the plastic strains are very smooth, even though they are only in the L2 space. So our formulation is very stable. Again, if we look at the iterations of the nonlinear solver, we can see now that indeed the first one requires more iterations because we are applying the finite strain nonlinear kinematics for our displacements. Comparing our results with literature, we get very good agreement. On the left, we see low displacement curve. On the right, we have a necking contraction versus displacement. Additionally, we compared with exactly same mesh using the standard nested approach implemented in MoFEM, and we get a perfect match. However, one thing to note that not everything is so great here. Towards at the end of the simulation, our method really struggles to converge, and it's because when plastic strains become dominant in the problem, this residual starts to scale very differently than others. So this is the issue that we will have to deal in the future. However, I will still present an example of flow forming as promised in the title. For that, we will use state-of-the-art contact formulation in HDIF space, details of which can be found in Andre's presentation later today. So the neat thing about this is that we can add contact Lagrange multipliers to our problem and solve it again as a one coupled system. So this is how it looks like. This is a small, let's say, toy problem that help us to identify the challenges that we need to face in the future. So if we keep rotating the mesh, we will have to use very small time step and also high refinement of the mesh in the contact zone to preserve the accuracy. So in the future, what we want to do is to utilize the LAE formulation when we decompose the motion into pure rigid body rotation and the deformation. And this is some first prototypes how it's going to look. So you can see without the mesh moving, we applied the contact, and we can see the movement of plastic strain. So only underlying material is rotating, not the mesh. Okay, in summary, our multifield approach solves plasticity as a coupled problem where plastic variables are degrees of freedom. It's monolithic. It gives us access to the material time derivative for LAE. It offers straightforward post-processing without the need of projection from quadrature point, and has a modular structure that can be easily extended with adding additional fields like temperature or Lagrange multipliers for contact as presented.